All right, before we get started, does anybody have any questions? I'm opening the floor, of course, to questions on chapters 1 through 7. Of course, in principle, you could ask chapter 8, which we haven't started. Chapter 7, we haven't completely finished, but that you can ask syllabus questions, test questions, and that kind of stuff. I'm in the process of getting ready to get started on work done by varying force, which I've sort of shown you a little bit. And of course, you guys might have questions regarding dot products, and the other name for that is the scalar product. So, anyone, feel free to type it in chat, or you can just speak out. The grades on campus, I mean, on a Canvas are potentially accurate. So what happens is when you go to set up the grade book, I've got the grade book set up correctly, but the problem is there's ways you can choose to calculate the grades. So in one case, and this is the case that I chose, basically it grades a grade anytime someone turns an assignment in. So it immediately counts that. And when it does that, it immediately counts anybody that hasn't done it, even though it's not the due date yet. Anybody that hasn't done it gets a zero. So there's really no quote unquote great way to make it accurate. That's why I offer you guys the Excel spreadsheet that's in the course, helpful links and documents. So if you keep track of it that way, that would be the most accurate way. That being said, it's accurate within that caveat that I just gave you. So I will look at them again tonight and make sure everything's up to speed. I'll send out an email, Jacob, after I do this just to confirm whether it is actually accurate or if I'm misremembering. But as far as I know, I got the grade book all set up properly. But like I said, you have some choices in the way you grade assignments when assignments aren't yet due, and whether you grade them at all. And then there's other choices too, and all of them have drawbacks. The way I've traditionally done it though is basically it grades a grade for a particular assignment as soon as people start doing it. But at that point, everybody that hasn't done it gets counted as a zero. So, your grade might be a little low. Yes, I did. I did push back the face-to-face test too. I thought I sent an announcement about that, but I might have just done it via the announcements in Canvas. In other words, I didn't explicitly say, "Hey guys, I wanted ahead and gave you some more time on face-to-face test too." What I did was change the due date because of some problems we had, and also just trying to help my students. And I clicked on notify students of the change, so y'all hopefully got that. And yes, I've decided to go ahead and let y'all have that extra time if you need it. Yeah, that shouldn't be a problem. And I sent them an email as well asking them to extend the due date through that date. So hopefully that's all working. I haven't received an email from them. Normally they'll send me an email if a student signs up for to take a test and they haven't gotten my proctor request yet. So I haven't received such emails, but again, I'll check them right after I finish here. I've been out working all day, so I literally haven't had a chance to look at anything other than like 5 o'clock this morning. Uh, I posted basically a new module as well as my lab for my physics 241001B. So, good question, Gabe. Anybody else have any questions? All right. Well, thank you all, especially. Actually, David, I did get your email too about the 242. I'm working to confirm that we can offer that next semester, but I'm really wanting to try to make the course better by offering a more robust online lab. We have the online labs that we made up for COVID, and that's what we're doing right now. That's not the best way, and you have to understand that Virginia Tech and UVA and NC State and Carolina, those schools are not necessarily going to accept those labs as the lab. So you may be forced, if you take this class, 241 like you are taking, not you guys in this NO2B, but the O01B class that does their lab online, they'll count the credit, but they just won't count it as the same as their lab. So they might actually go back and make you go back and take one of their labs. So I am trying to offer that in a more robust way. Uh, I would like to hear your opinions on it, though. Specifically, I would really like all my NO2B and my O01B students, if you guys could send me an email, let me know. Uh, I don't need a bunch of details, but I would like to know, do you have a smartphone? If you do, is it a Google phone? Is it a Samsung? Is it a Mac or Apple phone, iPhone, something like that? Just out of curiosity to find out what if students have smartphones, and two, if they have smartphones, what one do they have? And I think that was the main thing I needed to ask. Let me see, there was something else. Oh, if you actually got a lab that was completely transferable and would count, would you be willing to pay like a 50 or $100 fee for lab? That's sort of what I'd like to have you guys answer for me. I will send out an email. I'm going to try to remember to answer to send out an email after class to ask you guys that. But if y'all would be willing to offer that information, that'd be really helpful because that's what I'm shooting for. I have there's some books written and some whole courses made out where you can actually make an online physics lab where the student is not necessarily doing less than the normal lab student. In fact, the student tends to do a little bit more, but we would employ a Raspberry Pi or a Arduino microcomputer, and we would also use smartphones because there's actually a lot of free apps you can use with a smartphone. So all the stuff we're doing, for instance, with Logger Pro, where we take a video and then we analyze the video, you can do that on your smartphone immediately with a free app right now. So that would be the gold standard. If I could get to that point where we're doing that with the video, and I mean with the analysis, I would have to soup it up because you're not getting quite as much access to modern equipment. Like chances are you're not going to have a vernier caliper, you're not going to have all this electronic equipment. But once I integrate it with the Arduino or the Raspberry Pi computer, then we can buy dongles and possibly supply you guys with dongles so that you can actually do things like measure voltage and current and all that good stuff. But let me know what you feel about that. That's something that would be helpful. I know that wasn't a question you asked, but that's what I'm really shooting for. I also want to let's see if he's here. The other student's not here. There's a student that's really, really been super helpful. Like, soon as I post a lab, they immediately tell me, hey, well, it's usually within a day or so. They're like, hey, this video link didn't work or something like that. And you guys saw the O01B students, not the N02B students, saw that, for instance, the last week's lab had a link that you click in the addendum. Well, that link was a typo. Specifically, it had like a space on the end. So the actual address it read was 100% correct. But when you click on it, it thought the address was not that address, but that address with like a space on the end or something. Sometimes it'll be a missing letter, but I think this one I determined was a space. So, all right. Well, it looks like everyone's had the questions that they had for me answered. So I'm going to jump into work done by a varying force. One more time, does anybody have any other questions before I get started with work done by a varying force? Okay. Doesn't seem anybody's typing them or anything. Okay. So the work done by a varying force, I'm going to go ahead and share my screen with you guys. What we determined was a general expression for work, and that's something that's super helpful, and it's something that you can use for the rest of your career if you are, in fact, planning on becoming a physicist or a chemist or an engineer, that sort of thing. So it's certainly important. Not only that, we're going to learn some more stuff about how you actually create a potential energy function. So it turns out that once we know work, then we have an ability to create these from these conservative forces. We have an ability to create. My computer's not linking for some reason. Let me try undoing it. Stop share. So yeah, it turns out to be once you have a conservative force, and we'll explain exactly what that is. That allows you to create what we call a potential energy type function, and then that gives you a way to do all the physics that we've been doing with vectors, but now you can do them with scalars. So that's part of the conservation of energy that comes in chapter 8. Now I'm gonna try again sharing, see if it's working. Let's see if it comes up now. Oh, finally, now it's working. All right, so what we found so far was a dot product. So I want to reiterate that. So A dot B is equal to the magnitude of A, which we can write like this, times the magnitude of B, which we can also write like this, times the cosine of the angle theta, that is the angle between them. So I always like to have a diagram accompany that. So here's a vector A, here's a vector B, and when they're tail to tail, the smallest angle between them is the angle theta. You can see that that also turns out to be the component of A that is parallel to B times B. So that's another way of writing it. But there's also AX BX plus AY BY plus AZ BZ. And from that, that tells us that you can actually calculate the dot product using AX BX plus AY BY plus AZ BZ. And remember, that is a scalar. So I've seen students all the time, they'll do this computation and it'll be like 18i. No, there's no I hat in it. So just remember that you're sort of stripping off the I hats and the J hats, and in fact, you're stripping them off not because you're actually cutting them off, as you saw in the last class. I hat dot I hat is one, J hat dot J hat is one, K hat dot K hat is one, but I hat dot J hat is zero, I hat dot K hat is zero, and J hat dot K hat is zero. And if you reverse them, you get exactly the same result. So that covers all of the permutations that could possibly happen. So if you actually take the x component of A and multiply it by the x component of V and get a number, then you do the same thing with the y component of A and the y component of B, and the same thing with the z component of A and the z component of B. Add those three numbers up and you'll get just a plain number, but then you can set it equal to the magnitude of A times the magnitude of B times the cosine of the angle between them, and that allows you to actually determine the angle between them. So hopefully all that is fresh in your memory. And what we were able to determine was that the general formula for work is a line or path integral, and it's basically written as the integral from A to B of the force F, which could be a function of position. So it could be a function of X, Y, and Z, and then that is dotted with a dl vector. And what we're imagining here is you integrate along some path like this, and maybe you're going from A to B, or excuse me, that's supposed to be a lowercase b. Maybe you're going from A to B. So what you can do in that case is you can break this path up into little tangent vectors, and each of these little tangent vectors are vectors dl. And it's really hard to even see that they're tangent vectors because I make them so small, you can't see that they actually are parallel to the path at that particular point. But you do this and you break it up into all these little DLs. So this would be like DL1, and the next one would be DL2, and so on and so forth. But you also have to then calculate exactly what F is there. So there's your F. And then you have another F here. So this would be called F1 and this would be called F2. And it's not that it's a different force, but it's that the magnitude and the direction of the force could actually change in going from spot A, which is where F1 was, to spot just to along further along the path, a differential length along the path further away, the F could change. because, like I said, the f can be a function of position. So when you go to do that, you end up getting all these different f functions, and they might do crazy stuff like this, and so on and so forth. But the main thing is by being given the function as a function of the force as a function of x and y and z, for instance, you can figure out exactly what it is at each point, parenthesis x comma y comma z. And what you do is you splice up this path in small little divots so that basically it's so small that the force evaluated at the first end, at the tail of the DL vector, and the force at the head of the DL vector, and all the forces between the head and the tail of that first DL vector, all of those give you exactly the same dot product with DL1. If you've made the path, if you cut up the path small enough so that that's true, then you've made it small enough. If you find that still, now that you've cut the path into these itty bitty slices like this, if you find that f at the tail is slightly different, and what I mean by slightly different is if you want the accuracy to be 3 decimal places, then what you have to have is the force at the tail of the vector, and then the force at anywhere else between the tail of the vector dl and the head of the vector dl. If anywhere in there that force varies by more than plus or minus 1 in that 3rd decimal place, then you haven't done it small enough. So you then, cut it in half again or cut it to a tenth and so on and so forth. But that's the process. And we do that dot product. And you see that the dot product was chosen specifically because the dot product gives us a component of the force that happens to be parallel to the DL. Because any work we do that happens to be or any force we apply to something that has a component that is perpendicular to the path that we're actually trying to push the object along, then that component that's perpendicular isn't doing anything to contribute to the work. So the dot product, the f dot dl, gets rid of that perpendicular component. Does everybody have understand that or have any questions about that? Okay, so what I want to remind you about this is, again, when you do this integral, it is technically what we call a path or a line integral. And the way it's supposed to be done is you could imagine there's some kind of curve or some kind of function for this curve that you're choosing as the path. And it might be, a parametric set of equations that define the actual path that you're integrating along, and that's fine. Or you might have a literal function f of x, y, z equals 0, for instance, or f of x, y, z equals something other than 0. The main thing is all of those are ways to go about figuring out what the actual force is at various positions. So when you go to do this integral, you have to take the actual integral that you're computing and take the integrand, which is f dot dl, and establish that f dot dl as being on the actual path. So for instance, if you're doing a path y equals x squared, then your dx might, or your dy might be dy equals 2x dx, because you can tell if y equals x squared, then dy would be 2x dx, right? So when you actually do that, that gives you the ability to assign a path. Specifically, the path was along the line y equals x squared, which is a nice little parabola, and the dl would be that 2x dx. But in addition to that, for instance, if your function f of x, y, z has an x, a y, and a z in it, then you, to make sure that you're actually on the path that you're integrating along, you have to evaluate f by taking any value of y and replacing it with x squared, because that cements the actual force function onto the path that you're integrating along. Okay, so that's the major difference between just a regular integral and what we call a path or a line integral. Uh, but in addition to that, when you go to make this decision to do this integral or this path or line integral, then you've got to choose to either allow the DL to indicate which direction you're integrating along, or you allow the limits of integration, the a to b, for instance, to dictate which direction you're going, or to explain to the calculus universe exactly what direction you're going. But it's specifically very important that you do that exactly one time. So you either got to let DL indicate the direction you're going, and then the A and B just go from small coordinate to large coordinate. However, if you want to instead use the limits of integration to dictate which way you're going, then you might say you're going to integrate from B to A because you're literally going the opposite direction as what I've drawn on this diagram. So you do from B to A for the integral, but then the DL has to point in the positive coordinate direction, which we see is obviously, dy, dx, and that sort of thing. So you just take them as positive dx I hat, or positive dy j hat, or positive dz k hat. By doing that, you're not accidentally going to be off by a negative. So just keep that in mind. The good news is the vast majority of line and surface integrals that you do, you can completely not even know that they're line or surface integrals and get the right answer. But there's instances where you don't get the right answer because you didn't know what you were doing. Now, if you wanted to really think exactly what's going on, then you could say the work is equal to the integral. I'll leave off the limits of integration in the DL right now just to show you exactly how we can interpret f. So this would be f sub x, meaning the x component of f, and that x component of f could be a function of x, y, z. It could be a function of time as well. That we normally don't have to do that, but time could be in there. And then it'd be I hat plus f sub y. Again, that's a function of x, y, and z. J hat plus f sub z, x comma y comma z, k hat. That's just the f part. I'm going to put that in parentheses, and then we're going to say the dot dl is technically going to be dx I hat plus dy j hat plus dz k hat. And of course, you can then use the linearity of the dot product, and when you do that, you end up getting the integral fx dx plus the integral fy dy plus the integral fz dz. So again, like I said, this is what's going on with the actual integral. To make it a path integral, you would need to, if you're on the line y equals x squared, then every point that you see y in the function, you want to replace that with x squared. And then that actually sets the integral so that you're integrating along the path y equals x squared. Okay? So when I left you last time, I quickly did a derivation of the force on a spring, the work done in compressing a spring, once I gave you Hooke's law, which is the equation that tells us about the force that a spring applies to something. Now, I want to tell you guys that Hooke's law is not just about springs. It just so happens that if you wanted to even take something like this plastic Apple Pencil and you wanted to apply a force to it to compress it, you actually, even with this plastic, you're going to have to put enough force on it that it could actually become a dangerous situation. So you'd have to put so much force on it so that it would actually contract under this compressive force, or so much force on it to put it in tension so that it would actually cause it to stretch in such a way that we could measure it. When you do that, the force is so large that something could happen, like the pencil would fall off the edge of whatever is doing the pressing, and it would shoot off and possibly injure or kill somebody. So we don't necessarily want to work with 2x4s and Apple pencils and chopsticks to use Hooke's law, F equals negative kx. What we can do is instead do something a little more user friendly. So let's take the extreme case of not a solid object, but a solid object that's been coiled into the shape of a spring. When you do that, then it takes very little force to make the length of the spring change, whether you're stretching it or compressing it. What Hooke's law says is that F is equal to negative kx. And this I'm going to write it right here. This is Hooke's law, and Hooke was a one of Newton's many nemeses. So, for instance, Isaac Newton actually had a list of people that he did not care for. It's kind of funny. We There was an actual he had a ton of notebooks, and the notebooks. Many cases were written in some language that he made up with a bunch of symbols that he made up. And in order for you to even read them, you'd need to first crack the code of whatever language he's writing in, which sometimes meant he was writing from right to left or from bottom to top or something like that. And all sorts of weird words would be made up. But that's how he would hide what he was doing because he was constantly afraid that someone's going to try to steal his discoveries, and in fact, some people did. To this day, a lot of people think Gottfried Leibniz invented calculus, or at least co-invented it, but we have good evidence now to show that in fact Gottfried Leibniz had a friend and Isaac Newton had a acquaintance, that acquaintance actually went and visited Isaac Newton, and then within just a matter of weeks visited Gottfried Leibniz, and then Leibniz published his calculus, whereas Newton had called it a system of fluxions and all this sort of stuff. But it seems pretty obvious that that person probably gave Gottfried Leibniz enough information where he could really finish some thoughts he already had. I mean, he's obviously was smart enough to at least understand it. So, understanding it at that age, at that particular point in history, was a big feat of its own. So, it's not that he's stupid or anything, but he probably got a little bit of an idea of how it was done by this intermediary between him and Isaac Newton. Isaac Newton, of course, didn't like it. It was very upsetting to him, and that sort of thing. So when we actually did find his personal notebook, which was a really big deal, because we had his notebook on optics, we had his note, and I say notebook, it's actually many, many notebooks. He wrote over 500,000 words on optics alone. He wrote on the order of hundreds of thousands of words on the Bible, and had hundreds of thousands of words in notebooks on the Bible, all this good stuff. But we finally found his notebook that was the private, personal musings of Isaac Newton. And then we finally found the primer so that we could crack it, and people were really, really excited. Like the whole scientific and historical community is like, I can't wait to hear these great thoughts of Isaac Newton, because Isaac Newton was really like the most and I don't mean this in any way disrespectful, but more like what we think of as Quakers here in the United States, how they're very devout and they didn't do a lot of things that other people do because they thought it was not, praise to God, that sort of thing. So Isaac Newton was that kind of person. He really, really uh, loved God and all that good stuff. But we wondered what could this man that literally at the age of 70 something bragged about having never been with a woman, he never got married and all that stuff. So he was a very interesting person. Well, we got to it and we were very excited. And you get in like day one, it says, "Forgive me, Lord, for today I thought a bad thought," or "Forgive me, Lord, for today was the Lord's day and I worked when I shouldn't have." In other words, he worked on the Sabbath. It was just a ton of entries like that. And then all of a sudden you find, "Forgive me, Lord, for today I wish the death of 50 people." So it's like literally, I hate 50 people and I want them to die. So, anyways, an interesting character, but he was a nemesis of Hook, and one of the reasons that Hook was his nemesis is that Edmund Halley uh, postulated an idea. He said, "What kind of force actually allows orbits to exist around an object?" So, what kind of forces, like F equals some constant times x, F equals some constant times x squared, F equals some constant times x cubed, F equals some constant times x to the 1/2 power, all the different choices. And he put that out as a problem he'd like to know the answer to, and other people got involved as well, and no one really had an answer. And then they talked to Hook, and Hook said, "Oh, I've worked that out. Yeah, yeah, I've done that. I know the answer to that." And they said, "Well, tell us." He said, "Oh, no, no, I'll just show it to you." And he goes looking through his notes and all this stuff, and he can't find it. He said, "Oh, never, no, no, no big deal. I'll just redo it and give it to you, in a day or so." Well, they waited and waited and waited, and Hook never gave them the information. Then Edmund Halley went and visited Newton, and Newton did the same thing. Newton said, "Oh yeah, I've already worked this out. It's it's actually a 1/r² law, and also F equals kx. Both of those are capable of creating closed orbits." He said, "Here, let me show you." And he looks through his notes. He couldn't find it. He said, no bother. I'll just do it again and send it to you." So sure enough, he attempts to do it again and actually does do it again and turns it back into Edmund Halley. So we're pretty confident, for instance, that that is an incident where Hooke possibly stole information from Newton and took credit for stealing that information. He took credit for that information, even though he probably stole it. But it's not completely conclusive. But you can see that would make Newton kind of angry. And in fact, he was the head of the Royal Society. Hooke was, and then when Hooke retired from the head of the National Science Society, then Newton became it, and lo and behold, the only portrait of a head of the Science Foundation Royal Academy, excuse me, the only head who we don't have a portrait of is Hooke's. so, almost certain that Newton got rid of Hooke's portrait just out of anger. So, anyways, nice little backstory, but Hooke was a very good scientist, no question about it. And one of the things he discovered was that if you put an object in compression, then that force of compression, F, would actually act in the direction negative K times X. Where what he's saying is if you apply a force to a beam or to a 2x4 or to an Apple Pencil, squishing it like this, right? Then the pencil pushes back with a force in the opposite direction. That's why the negative sign is in there. And that is equal in magnitude to some constant times x, the amount of compression that the object sustains. So, for instance, by compressing this, it might have been 8.2 inches before, but now when you put it under compression, maybe it's 8.1 inches, right? So that compression is something that's real. If you in fact also did it in tension, then that would tend to make it a little longer. But lo and behold, if you're pulling upward, then the pencil is going to pull downward. Again, that's why they said F equals negative kx, and that's Hooke's law, and it's about everything, not just springs. And again, as I told you, that's why we do springs. Okay? So that is actual Hooke's law, and we can use that now to understand springs. So, for instance, if we draw a spring system, we can imagine this is our x-axis, for instance, and this is our y-axis. I can imagine that this y-axis also corresponds to a wall on which a spring is attached. And it has a mass, say, at the end of the spring. And what you can do is you can apply a force F this way, and that force F is going to tend to elongate the spring. Okay, in so doing, the spring will become slightly longer, and that amount of lengthening is directly proportional to the force. So, for instance, if you use a force of zero point 0.1 newtons and you get a stretch of 1 centimeter, then if you use a force of zero point 0.2 newtons, you're probably going to get a stretch of 2 centimeters. If you use a stretch of zero point 0.4 newtons, you're probably going to get a stretch of 4 centimeters, meaning it's directly proportional. Okay? So that's what they ultimately did. And you can see now that this would be the normal position of the mass in the spring, but upon stretching it, I'm going to use a different color pen now. The spring gets stretched further and further and further until the mass here is m. And what Hooke is claiming is that this distance x is given such that x is equal to F over K. Okay, so what I want to do now is calculate the work done in stretching a spring and amount X, and it's going to turn out that you can also calculate the work done in compressing a spring as opposed to stretching it. So work compression, so I'll just write COM for compression, is equal to the integral from A to B of f dot dl. Now, in this case, we know that when I apply a force F that causes a stretch X for a spring that has a spring constant K, then the spring is going to respond in the opposite direction with a force negative K times X, right? If I were to apply a larger force, then the negative K times X is going to get larger as well. So what we want to do is apply just enough force to overcome the force that's fighting the stretching or the force that's fighting the compression. And when I do that, that means I'm going to have the force be equal in magnitude to the Hooke's law force. But Hooke's law says F equals negative kx. We're actually applying F in the positive x direction, say for tension, or in a negative x direction, say for compression. And the force is going to be F is equal to negative kx in compression, and F is equal to positive kx in tension because we want it to be the direction of the force. So if I do this now, I can say, well, the force is going to be equal in magnitude to K times X. And I'm going to integrate from X equals X0. And what I mean by that is in equilibrium, the mass on a spring would have a length x0. In other words, there's some arbitrary point where you could measure the distance from the wall to, say, some part of the spring or to some part of the mass that's on the end of the spring or whatever. And as long as you consistently do that to the same spot, you shouldn't run into any problems. What I'm saying is that spot that we're going to measure with respect to is x0. Okay, so we're going to imagine integrating from x0 to some new x, which I'll call x0 plus x. Okay. Now, I've just, even though I didn't say it out loud and didn't warn you about it, I just chose the direction of integration to be indicated by my limits of integration because I literally said I'm going to start from x equal x0 and then end up at x equal x0 plus x. Okay. So I've already said the limits of integration are actually going from where we started to where we ended. That means now I have to write the dl in the direction that in the positive coordinate direction that we're moving. So since we're moving in the x direction, whether it be positive or negative, I'm just going to have to write it as dx I hat because I already indicated the direction with the limits of integration. Notice how it's completely irrelevant here though, because they're both positive, right? So if if I had decided to let dl indicate my direction, I would have written dl is equal to dx I hat because I'm going in the positive x direction. Well, then I'd say, okay, well, the limit of integration has to go from small x to large x, so I'm going to go from x0 to x0 plus x. So that's why the vast majority of the times you never have to even worry about it being a line integral. You should always, but you don't have to because a lot of times you're going to get the right answer. So we're applying a force that is equal in magnitude to the restorative force that Hooke predicts. That's why it's equal to kx, and it's going to be in the I hat direction. So I'll put I hat after the kx. Then I'll put the dot product, and since I already indicated the direction of integration by writing out the limits of integration in the exact direction we're going, I'm going to write dl as dx I hat, which is in the positive coordinate direction. So that's it. I've got it completely done. I'm now going to integrate these two. And the way I integrate it is I first use the linearity of the dot product. And the linearity of the dot product just means that in this case, I have a vector that's kx I hat. I can put parentheses around it so you can see it better. That's one vector. And then I have another vector dx I hat. The fact that it's linear means that I can take that dx and put it right next to the kx on the other side of the first I. And if we did it in the opposite order, if I wrote it as dx I hat dot kx I hat, then I could pull that k out in front and have the dx times k times x I hat dot I hat. So that's what I mean by the linearity. In this case, that's going to become k times x dx times I hat dot I hat, and I hat dot I hat, we know from this, has to be 1 times 1 times the cosine of 0 degrees. That's because anytime you see a vector, unless they explicitly say otherwise, but anytime you see a vector with a little hat on it, that vector is understood to be a unit vector. That means its magnitude is 1, not 1 meter, not 1 Newton, not 1 joule, not 1 anything. It's just 1 unit. Okay? So if I take the dot product of I hat dot I hat, as I said, that becomes 1 times the cosine of 0 degrees. And of course, that is equal to 1. Okay? Now I can just get rid of that completely because it's just 1. And I now know that the integral of kx dx is 1 half. Whoa, just switched to my laser pointer. Is 1 half k x squared. Now, in principle, what that means is k times x0 is actually going to be 0. So just keep that in mind because that's the nature of x0 being the equilibrium state. Now I have to evaluate that at the limits of integration, which is x0 and x0 plus x. So when I do this computation, I get 1 half times k times, now I'm going to say x0 plus x squared minus x0 squared. Okay. Now, this is a lot longer, more convoluted way than you see in your textbook, but I'm just trying to show you that it's a line integral, that it's a path integral, and sort of all the gory details. No one would ever write it the way that I just did. People don't write integrate from x equals x0 to x equals x0 plus x. They just say, they would put the origin, for instance, at the equilibrium point, and then they'd say they're going to integrate from x equals 0 to x equals x. That would be perfectly fine. Now that I've done it this way, though, I want to show you how it works out. So 1 half kx, 1 half k. Now I've got to square the binomial here, so I have x0 squared plus 2x x0 plus x squared minus x0 squared. And you can see already that the x0 and the x0 is going to cancel out. And since we know f is equal to k times x0 is equal to 0, then we know that this term right here is going to produce 0 once we multiply it by 1 half. So again, carrying on, we're going to have 1 half k x squared. Now, what I just chose was to take this term right here because I know that's the one that's ultimately going to survive. This one's not going to survive, so I wanted to have the answer up front, so I pulled this one out first. Now I'm going to evaluate this term, and when I evaluate that term, it's going to be plus 1 half k times 2x x0, which you can see is going to be k times x0 times x, but, and that's plus 1 half kx squared. Sorry about that. 1 half k x squared. Plus, like I said, when I carry that 2 through, I'm going to get k times x0 times just plain x. But since x0 is the equilibrium position, k times x0 is 0. So the actual work done in this case, I said compression even though I worked it as expansion, as stretching. But anyways, in this case, we just get the answer is 1 half k x squared. And since I did start off doing this for compression, but then ended up deciding to do it for tension, I'm going to change this to tension. Okay, so by stretching the spring. In other words, I found out that if I move it from its equilibrium position a distance x, then the work done is equal to 1 half kx squared. And that's a formula now that we can use. So in addition to these formulas I wrote up top, you now have another formula, actually a couple of other formulas. They are F is equal to negative kx, which is Hooke's law, and they're also work equals 1 half kx squared. So these are also two new equations we worked out. You don't have to go through and do this integral every time anymore. So whenever you run into a spring and you know that some process is going to cause the spring to stretch a certain amount from its equilibrium point or to compress a little amount from its equilibrium point, then you know the work required to do that is 1 half k times the distance from the equilibrium that you move it. So 1 half k times x squared. Any questions on that? All right. So let's look at an example. This is just like example 7.5. So I'll write, if you have your book available, that'd be a really good thing to look up because I'm going to read it to you and I'm going to work it out, but I'm not going to write it out because obviously that takes a long time. So this is called work done on a spring, example 7.5, and part A says a person pulls on the spring in figure 17, or excuse me, figure 710, stretching it 3 centimeters, which equals X max, which requires a maximum force of 75 newtons. Actually, I think I did this in the last class. Let me double check. Anybody remember, did I work that problem last time? Because I'll do the next one instead if I had. Let's see. I did 7.1, 7.2, using the dot product, worked on a spring. Oh, yep, I did work this one, so I'm going to skip to the next one. So let me say this is not going to be 7.5. We're going to go instead to a different example. Ah, darn it. I changed my pencil to a eraser and it just turns it back. All right, so it looked like the other example that I was going to do. I don't know where that went. Let's look and see if I can find it on a different place. No, that's not it. That example doesn't help me. I know exactly what example I want to do, but I'm not finding it. And it's almost like I'm wondering if I'm remembering an example that was in the previous edition of the textbook, but not this new edition, because I don't think that's the case, though. Let's see. Nope. It's just not here. It's probably in chapter 8. That might be the reason why. So, anyways, we'll skip this example. Uh, oh, is this it? Oh, yeah, there it is. Okay, so here's an example. It says a more complex force. This is 7.6. I don't know why I didn't see it just now because it's literally the one right after it. But it seems like it might have been in a different section or something, or maybe I guess maybe my page didn't load completely by the time I tried to scroll up, and that made it disappear. So here's example 7.6. It says force as a function of x. A robot arm that controls the position of a video camera, figure 7.12, is an automated surveillance system. Is in an automated surveillance system is manipulated by a motor that exerts a force on the arm. Assume that the force is given by, and here goes my force, f of x. That means it's a force function that only depends on the variable x, and that's equal to some constant f0 times 1 plus 1/6 x squared over x0 squared. So that's the actual formula. It says where f0 is equal to 2.0 newtons, it says x0 is equal to 0.0070 meters. And x is the position of the end of the arm. If the arm moves from x1 equals 0.010 meters to x2 is equal to 0.050 meters, then how much work is done? So that's the whole problem. Let me read it again to you. A robot arm that controls the position of a video camera, figure 712, in an automated surveillance system is manipulated by a motor that exerts a force on the arm. Assume that the force is given by f of x is equal to f0 times parentheses 1 plus 1/6 x squared over x0 squared, where f0 is equal to 2.0 newtons, x0 is equal to 0.0070 meters, and x is the position of the end of the arm. If the arm moves from x1 equal to 0.010 meters to x2 equals 0.050 meters, how much work is done? So we're going to compute it like that. Solution. What we know is the formula for work, and that is work is equal to the integral of f dot dl. Okay, that's the most general expression. And we know in this case it's all one-dimensional motion, so the dot product is almost moot. We're basically just saying f is pointing in either the positive x direction or the negative x direction, and you can only tell that when you put in a specific value of x. And then we're obviously moving it from x being a positive value to x being a larger positive value. So we're obviously moving it in the positive x direction. So I'm going to say work is equal to, in this case, I'm going to go ahead and take the F0 and pull it out front because it is just a constant, 2.0 newtons. And now I've obsessed over it so much that I wrote a really bad version of F0. Now I'm going to integrate from x1 to x2 of 1 plus x squared over 6x0 squared. That is going to be dotted. So it'd be that times I hat will be dotted with dx I hat. Again, you're just going to pull the dx next to it, and the I hat dot I hat is going to be 1. So why waste our time? We'll just say dx like that. Now you can distribute the dx, and then you'd break the integral up into two separate parts. So I've got the integral from x1 to x2 of specifically just plain dx. That's for the first term, the 1 to the left of the plus symbol. And then after the plus symbol, we still have the f0 out in front. So I'm going to have f0 integral from x1 to x2. Now this time I'm going to say, let's put 6x0 squared in the bottom and pull that out in front because that's just another constant too. And in this case, oh, there it goes, turn into an eraser again. And in this case, it's going to be x squared dx. Now, the integral of dx is just x, and then we evaluate it at x2 and do subtract from that the evaluation of it at x1. So this is all going to be basically f0 times x2 minus x1. And then the other integral is going to be f0 over 6x0 squared. And the integral of x cubed is 1/3 x, excuse me, the integral of x squared is 1/3 x cubed. So I'm going to say 1/3. And now I have to evaluate the x cubed at x2. So that'd be x2 cubed minus x1 cubed. So that's basically the entire calculation we got to do. Now I just got to put in the numbers. And we have 2.0 newtons times 0.050 meters minus 0.010 meters. That's for that first term, plus 2.0 newtons. Now this time I've got a 1/3 and a 1/6. So they're going to multiply to give me 1/18. So I'm just going to write an 18 in the bottom. And I'm also going to write the x0, which is 0.0070. and that's in meters, of course. And I'm going to write that, and of course it's going to be squared at the bottom. So now I've accounted for the 6, the x0 squared, and the 3, but now I've got to take, oh, there I go again. I'm really getting sick of this program doing this. It's aggravating the heck out of me. All right, so now, there it goes again. So now it's going to be 0.050 meters cubed minus 0.010 meters cubed, and then square bracket. So 0.050 minus zero point zero 0.01 is obviously 0.04. Whoa, my fat finger hit a 3, hit a 2, and I ended up getting the answer of 0.03. And I was like, whoa, that's not right. So now I'm going to take that 0.04 and multiply it by 2, and that's obviously going to give us 0.08. So this first one is 0.08, and we can see the units turn out to be zero. For starters, sig figs are going to turn out to be two of them. So 0.80, and then the units are Newton meters, and of course a Newton meter is a joule. So I'll leave it as a Newton meter right now. Now I'm going to take the 2 divided by 18 divided by 0.007 squared and put that out in front. So 2 divided by, I'm using parentheses here, so I wanted to read that out. So 2 divided by parenthesis 18 times 0.007. Now I'm going to square that and then close parentheses. If I didn't put that parenthesis there, what's going to happen is your calculator knows the rules or the order of operations better than you do, and therefore it's going to say, "Oh, I need to take that 2.0 newtons and divide it by 18, and then take that answer and multiply it by 0.0070 meters squared." But that's not what you want, right? But that's what order of operations says, unless you put the parentheses here. So now I've got all that, and that gives me a really big number, 2,267.6. So I'm going to say plus 2,267.6. And in this case, the units turn out to be newtons per square meter, but it's only two sig figs, so really those last three digits are not sig figs. Now I've got to take the 0.050 and I got to cube that. So I'm going to raise it to the third power. And then I'm going to subtract from that 0.010, and that too is going to be cubed. The 0.050 cubed is 0.000125, and the 0.010 cubed is 0.000001. So anyways, the result is all of this is going to be multiplied by 0.000124 meters cubed. Now we can see that the meters cubed multiplied by the meters squared in the bottom is going to cause the meter squared to disappear, and the meter cubed is going to be replaced with just a meter, and then that's going to be multiplied by a newton, and therefore we're going to get a newton meter again. So I take the 0.0012 or 0.000124 cubic meters, multiply it by the 2,267.6, which is more than enough sig figs, and that gives me, we already had the 0.080 joules. Now we have the 0.2812 joules. Now, again, it's only good to 2 sig figs, so that means it's only good to the hundreds place, whereas the first term was actually good to the thousandths place, but it doesn't matter. We still managed to get 2 sig figs. So 0.28 plus 0.08 gives 0.36 joules. Any questions on that? Boy, that was a lot of talking by Mr. Younger. No questions? All right. So now we're going to move on to work, the kinetic energy and the work energy principle. I want to start with a sort of quick derivation. So we learned, for instance, in Newton's laws, remember Newton's three laws, and remember they are laws. So I tell my students probably 10 times a semester that if you're ever taking a class and something's named a law or a whole chapter or a whole section within a chapter is named as the name of that section or the name of that chapter, there's a good chance that you should commit that to memory. Okay. In fact, I would just say generally you'd be crazy not to, because sometimes some teacher's going to be really nice and say, hey, here's 5 points, or hey, here's 15 points on this test. All you got to do is state Newton's laws of motion. And lo and behold, as a teacher, I've done this, and lo and behold, I get, 40% of the class gets 15 points that were supposed to be free credit, not credit. Okay. So always do that. So Newton's first law, an object in motion tends to stay in that state of motion unless acted upon by a net external force. But the other one, the second one is the one I'm shooting for, and that's the net force, or the summation of all the forces is equal to mass times the acceleration. Okay, and then the third law, of course, for every action there's an equal but opposite reaction. So the fact that Newton's second law has a net force on the left-hand side, it's the sum of all the forces is the left-hand side, equals mass times acceleration, that's the right-hand side, makes me think, I wonder what the net work would do. In other words, if you calculated the work done by the net force, what would you get? Well, that's what we're going to start off with. So work net is equal to the integral. Remember, work in general is F dot dl, but I'm wanting to know the work net. So I want to take the left-hand side of Newton's second law, which, remember, Newton's second law is the summation of forces equals m times a. So I'm going to write the summation of the forces dot dl. So that is actually the net work done on a system, where I'm now calculating the net external forces acting on the system as sigma F, and using Newton's second law, which I'll call N2, which says the summation of forces is equal to MA, which MA is M dV dt. Okay, so now I can take this and put it up there, as I do right now. Watch what I'm doing. I'm going to take the integral, instead of sigma f, I'm going to now replace that with m dv dt. So I have m dv dt dotted with dl, like that. Okay. Now, here's something that you might not know, and in fact, I didn't know when I, was taking the same course, and when I finished calculus, I didn't know it. Most people don't get to go far enough in calculus in their calc course at college to do this. If we went to, Harvard, Princeton, or Stanford or something like that, we probably would. Or in some cases, I've actually discovered that often those upper echelon schools don't even offer the lowest, rung of the math ladder, and sometimes won't even offer, say calculus. Uh, I've seen schools like this occasionally, and what they're offering is really advanced calculus. So you just start off in your freshman year taking what they might call calculus, but it's really advanced calculus. And when you do that, you're actually going to learn that these dVdt's that we use for actual calculating a derivative, they are mathematical entities in themselves. So, for instance, the dVdt looks like just a neat little formula for something that's like a slope. Remember, that's what the idea of calculus was. The derivative is the instantaneous rate of change, and therefore it's the slope. So dVdt literally looks like change in v over change in t. But it turns out the dv is a thing all by itself. You can call it a one form, one O-N-E, hyphen form FORM, which is sort of like a brother of the vector. Okay, there's a vector, and then there's something dual to it. That's the fancy word we use. And the thing that's dual to a vector is a one form. And then a whole branch of mathematics opens up that you've never heard of. So I'm going to tell you, and this is the reason I'm telling you that, I'm going to do something weird here, and you're not necessarily going to like it. And I'm telling you that we can do this specifically because you don't know enough yet to realize that this is perfectly reasonable. Okay? So what I'm going to do is I am going to take that dt and move it to be under the dl. So it's going to get the integral m dv dotted with dl dt. But then if you think about it, you realize, wait a second, isn't dl dt the velocity? And you would be exactly right. You can tell by the units that it is, but we're literally taking the instantaneous rate of change of the length that you travel along a path parallel to that length of the path, right? So it's literally the velocity. So this becomes m dv dot v, which dot products, of course, are you're able to reverse them. So I'm going to write this as mv dv. And what I did, in addition to reversing their order, is I went ahead and evaluated the derivative, or excuse me, the dot product, and the dot product of vector v and its differential v is just v dv. Well, the integral of mv dv is 1 half m v squared. And therefore, if you wanted to imagine doing this from, let's say, x initial, I don't want to write it that way, x initial to x final, then you would write that limit of integration as x initial and x final. But that doesn't make much sense now because the variable that we integrated with respect to has completely changed from the dl to a v. So it would be better to go ahead and call this from, oops, dang it, there it goes again. Oh, heck, the sparklers. Stop that. Okay, so that integral mvdv is going to be from v initial to v final. That means I have to evaluate that integrand, or that integral that I just calculated, between VF and MV, or between VF and VI. So this is going to be 1 half MV final squared minus 1 half MV initial squared. And lo and behold, we can take kinetic energy K and define it to be 1 half MV squared, in which case we've now came up with the work energy theorem. And it basically says the net work done on any system is equal to the change in kinetic energy. That is the work energy theorem. Now, what this means, one way of looking at it, anyways, is that you were here Wednesday of last week, roughly this time, and you were probably sitting at a desk somewhere. And now, there's some chance that you might have been driving somewhere, listening to the lecture. That happens. I don't recommend doing that. That's a dangerous thing. Don't do that. Or it's a thing that makes you, miss a lot of stuff because you're, doing the right thing and paying attention to the road. But either way, in principle, you were probably sitting still. Therefore, your velocity then was zero. And now today you're probably sitting still again, so your velocity again is zero. So I can tell you for a fact that the total work done on you since Wednesday is zero. Okay. Now that counts the work that you did in getting up from your desk when you're finished with class. That counts the work you might have done when you went and climbed on a stair climber and worked out, for an hour or whatever. That includes your walk up to the top of Mount Trashmore. All that work done, all that stuff that happened, doesn't matter. You don't have to know it. You don't have to know, but you know that in total, the sum of that work was zero. Any questions on that? All right, so let me go ahead and show you an example of how we use such a thing. And what we're going to do is jump to example 7.7 from your book. I think I can fit it right here, so I'm going to go ahead and say example 7-7. Again, I'm going to read it to you and work accordingly. So example 7-7, kinetic energy and work done on the baseball. A 145 gram baseball is thrown so that it acquires a speed of 25 meters per second. A, what is its kinetic energy? And B, what was the net work done on the ball to make it reach the speed if it started from rest? Okay, so that's a pretty straightforward question. Let me read it again. A 145 gram baseball is thrown so that it acquires a speed of 25 meters per second. A, what is its kinetic energy? And B, what was the net work done on the ball to make it reach the speed if it started from rest? So I'm now going to write down what I know. I know V initial is equal to 0. I know V final is equal to 25 meters per second. I know that the mass of the ball is 0.145 kilograms. So notice I went ahead and put the unit in the appropriate, or put the mass in the appropriate unit. Uh, that's just something you have to do. Remember, we're using these equations. They're all supposed to be have their values entered as the SI base unit. Okay. There are times where you can put the prefixes in too, but you got to pay close attention to that. So I wouldn't recommend doing it yet. Now that I have that, we want to first say what is its kinetic energy. So K equals question mark. That's part A. And then part B, they want to know what was the net work done. So W net equals question mark from V initial to V final. So that's the two questions we're going to ask. Uh, I'll go ahead and say solution. Kinetic energy is defined to be 1/2 mv squared. The work energy theorem says that W net is equal to the change in kinetic energy. And of course, the change in kinetic energy is K final minus K initial. And remember that delta, that triangle that I drew here, that is something that always means final minus initial unless we explicitly tell you otherwise. So keep that in mind. No matter what follows the triangle, that symbol is going to be written as final, and then that symbol is going to be written as initial, and you're going to do the final minus initial whenever you see that delta, that triangle with a symbol next to it. Okay, unless we explicitly tell you otherwise. So for part A, we've got K equals 1/2 0.145 kilograms times 25 meters per second, and 0.145 times 0.5 times 25 squared gives me 45.3125. I'm just going to say 45.3 because we only have two sig figs. Wait a second. Yep, they only have two sig figs because of 25. So I'll call it 45.31. And notice the units are kilograms, meters times meters. Remember, because it's meters squared, I chose to write meter for a reason that you'll see in a second. So kilogram, meter divided by second squared. Can anybody tell me what a kilogram meter per second squared is? Let me check my chat. Ooh, I got chats. Okay. There were chats, but it wasn't related. So the kilogram meter per second squared, notice that's mass times, exactly, Ellie. That's mass times meters per second, which is acceleration, and mass times acceleration is obviously force. So yeah, that's an actual Newton. I'm going to underline the 3 and the 1 because they're not sig figs. So this is 45.31 Newton meters, which we learned already was in fact a joule. So the kinetic energy is in fact 45 joules. So that's the answer to part A. Any questions on that one? All right, for part B, work net is equal to change in kinetic energy. Well, change in kinetic energy is kinetic energy final minus kinetic energy initial. Well, kinetic energy final is 45.31 joules, and kinetic energy initial is 0.0 joules. Therefore, we can say W net is exactly equal to the same 45 joules. Any questions on that? So that's an application of basically the work energy theorem. It's a simpler case because they just said, what's the total work done and, accelerating this baseball up to 25 meters per second. Uh, Easy enough. It's just changing kinetic energy. That's the definition of the work energy theorem. Let's look at example 7.8 now. No questions on 7.7? So here we go with example 7.8. And example 7.8 says, work on a car to increase its kinetic energy. How much net work is required to accelerate a 1,000 kilogram car from 20 meters per second to 30 meters per second? Straightforward enough. How much work is required to accelerate a car? So that means a car, a 1,000 kilogram car. So that means the mass is 1,000 kilograms. Now, your book calls that quantity ambiguous, so hopefully y'all have run into that type of question on various practice tests and or face-to-face tests, okay? That's what they're shooting for when they're asking you what is the number 500 in terms of how many sig figs it has. The answer is ambiguous. So this is a case, again, it's ambiguous, but I'm going to call it 4 sig figs just because I can, okay? I know that the initial velocity is equal to 20 meters per second, and I'm going to treat that as if it's 2 sig figs. And I know that the final velocity is equal to 30 meters per second, and I'm going to treat that as 2 sig figs as well. And again, what they want to know is what is the net work done. So, solution, work net using the work energy theorem is equal to delta K, and K is equal to 1/2 M, whoa, V squared. Now that I have that, I can say K initial is equal to 1/2 times 1,000 kilograms times 20 meters per second, and that's got to be squared. So I'm going to say 0.5 times 1,000 times 20 squared, which obviously we can do all that math in our head, but we don't need to. This is 2.0 times 10 to the fifth. And of course, that works out to be joules, as I just showed you in that previous example. So kilogram, or final kinetic energy KF, is 1/2 times 1,000 kilograms. This time it's at 30 meters per second, though. So the fact that we know delta K is K final minus K initial, that obviously tells us we need to calculate K final and K initial. That's why I'm doing that. And in this case, it turns out to be 0.5 times 1,000 times 30 squared. And that's 4.5 times 10 to the 5th. So again, remember I assumed the 1,000 kilograms was 4 sig figs. I assumed the 20 meters per second was 2, and I assumed the 30 meters per second was 2. So we're really only getting 2 sig figs out of that. That's why I wrote it as 2.00 underbar and 4.50, or yeah, with the underbar on the zero. Okay. So now I can say that work net for this particular car is K final minus K initial, which is 4.50 times 10 to the fifth joules minus 2.00 times 10 to the fifth joules, which is obviously 2.50 times 10 to the fifth joules. So that is our work net work done. Anybody have any questions on that? Okay. So there's a really nice conceptual example. It's called Conceptual Example 7-9. I'm going to read this out to you and we're going to talk about it a little bit. It says Conceptual Example 7-9, work to stop a car. A car traveling 60 kilometers per hour can brake to a stop within a distance of d equals 20 meters. If the car is going twice as fast, i.e., 120 kilometers per hour, what is the stopping distance? Assume the maximum braking force is approximately independent of speed. So, what we're thinking about here might not jump out as to you as a work energy theorem problem, but that's because you just learned about the work energy theorem. So, you probably don't have a real sense of exactly where and when we use the work energy theorem. I will tell you, and I hinted to you last time, that the work energy theorem is the method that we use whenever you see a police officer out measuring the skid marks at a wreck. They're actually measuring it so they can figure out exactly how much work was done by friction against the car, and that work done by friction was basically enough to take it from the kinetic energy that it had to a kinetic energy very close to zero. So from that, you can determine exactly how fast the car was going when it got in the wreck. So in this case, we're imagining that the velocity is 60 kilometers per hour. Doesn't matter that we don't have it in meters per second because we're not actually doing the calculation. But what we do have is the fact, and I'm going to separate this from the rest of what I was talking about since we've already finished that example. What we do have is the net work is equal to the change in kinetic energy. Okay. Now, the net work in this case is a car coming to a stop. Okay. Now, the force that actually does that is basically a friction force, and you can sort of think of it as a friction force between the road and the tire, in which case the friction force is acting the opposite direction as the velocity because that's what they do, of course. And by adding that extra force backwards over a distance, we get the work net is equal to the friction force times the distance. Okay, the friction force obviously is mu times the normal force, and then of course if it's a static situation, which means the car's not skidding, so yeah, we're gonna have to use static friction. Static friction has a max value of mu times the normal force, whereas kinetic friction is always mu times the normal force. So we have that, but we also have change in kinetic energy, delta K, is equal to 1 half m. Now we're going to say V final squared minus V initial squared. So what we can see now is that D is proportional to the square of the initial velocity. Okay. If we're bringing it to a stop, what we know is K final is equal to 0. And because of that, we see that the normal force, and by the way, I really should have written negative FD. I hinted at it as I was talking, but I just didn't write the negative. And it now makes sense because the negative FD is exactly the reason we got 1 half M times negative V squared. So what we have is negative D is directly proportional to VI squared. So to answer the question, it says a car traveling 60 kilometers per hour can brake to a stop within a distance of 20 meters. If the car is going twice as fast, what is the stopping distance? So Twice as fast means V went up by a factor of two. If V goes up by a factor of two, then D has to go up by a factor of two squared, which is four. So you'd expect D to be not 2 times 20 meters, but rather D to be 4 times 20 meters, which would be 80 meters. Any questions on that? Now, just to mention, I told you I saw an actual chat. Adrian asked me, "You can't write the dot product in unit vector form." No, that's sort of the whole point. Is in calculating the dot product. Let me show you the version where we did last time. In calculating the dot product, this is the actual process, and you can see in this actual process that we're actually calculating it with the I hat for the AX and with the I hat for the BX and with the I hat for the AX and the J hat with the BY and all that good stuff. And then we use the linearity of the dot product to get AX BX times I hat dot I hat. But the weird part is the AXBY becomes zero, or not the AXBY becomes zero, but that term becomes zero because it's I hat dot J hat, and the angle between I hat and J hat is 90 degrees. So you did actually technically write it in IJK notation, but when you once you actually get the formula, you can see it does not have any I's or J's or K's, and it should not. Okay, so this red boxed off area is exactly the way it should be written, with no I hat, with no J hat, with no K hat, and if you ever have an I hat, J hat, or K hat in a dot product, you can just go ahead and assume that you did it wrong. Okay. But thanks for asking that, Adrian, because that is the number one often made mistake. And yes, hope you were right. It was the Newton. Thank you. Anybody have any other questions? All right, here we go. A compressed spring. This is example 710. I'm going to go back to our notes. That would be helpful here. I'm going to write on here that this was conceptual example. Whoa. Okay. Now, example 710. Example 710 says a horizontal spring has a constant K equal 360 newtons per meter. I'm going to treat that as three sig figs, even though they might have meant two. How much work is required to compress it from its uncompressed length, x equals 0, to x equals 11.0 centimeters? Be careful with this, by the way. When you're dealing with springs, sometimes a motion as big as 11 centimeters could literally spring the spring so that it no longer has a nice F equals KX relationship. So just from a practical standpoint, watch out if you actually exceed the limits of a spring, it's almost always obvious that you've done so because it will no longer like shrink back to the original size it had. So that's something to keep in mind. So again, a horizontal spring has a spring constant 360 newtons per meter. How much work is required to compress it from its uncompressed length x equals 0 to x equals 11 centimeters? B, if a 1.85 kilogram block is placed against the compressed spring and the spring is released, what will be the speed of the block when it separates from the spring at x equals 0? Ignore friction. So we can imagine that's like a box on an ice skating rink. And then C, repeat part B, but assume the block is moving on a table as shown in figure 718, and that some kind of constant drag force, FD equals 7.0 Newton, is acting to slow it down, such as friction or perhaps your finger. Okay? So I'm going to write down everything we know. What we know is K, oops. What we know is K is equal to 360 newtons per meter. Notice that is the unit that we expect for K from Hooke's law. We also have that it's moving, and we want to know how much work is required uh, to compress it from its uncompressed length. So I'm going to say x equals 0 to 11.0 centimeters. That's in part A. So I'll just put an A up there. So that's some information we know. And they want to know how much work is done. And then they say in part B, if a 1.85 kilogram block is placed against the compressed spring and the spring is released, what will be the speed of the block when it separates from the spring at x equals 0? So in this case, we have M equals 1.85 kilograms. So this is a 3 sig fig number. That's kind of helpful. And they're imagining putting it against the compressed spring and then letting it go. What's going to happen is, according to Hooke's law, since the spring has been compressed, which would be a force, let's say, according to the diagram, that would be a force pointing to the left. That's actually did the compressing. Therefore, Hooke's law says a force to the right is what the spring is going to supply. So that's going to be a force to the positive x direction or to the right. Okay. And what's going to happen is it's going to push that spring, or excuse me, put the spring is going to push that mass along the table surface until it reaches the equilibrium point. And at that point, the spring is going to start slowing down because it's not hard fixed to the actual mass. It's not like tied to it or anything like that. It's just up against it. So the spring is going to continue past x equals 0, but it's going to start slowing down immediately because it's got that Newton or that Hooke's law force pulling back on it. That's going to tend to slow it down. Whereas the box, which has no friction, is going to continue moving on at whatever speed it reached at that x equals 0 position. So what we're wanting to know there is what will be the speed. So I'm going to say V final equals question mark. That's for part B. And then repeat part C if the block is moving and, or excuse me, if the block is moving on a table with some kind of constant drag force. So C, FD is equal to 7.0 newtons. Okay. So solution, we need obviously uh, work or energy. Later we'll call this a potential energy and we'll use the symbol U. So work or energies will equal to 1/2 kx squared. That's how much work is done in compressing or stretching a spring by an amount x if the spring constant is k. We also could say, for instance, that work net is equal to the change in kinetic energy, and that's just the work energy theorem. So we'll start off with part A, where they just, of course, asked us how much work is required to compress it. So work is equal to 1/2 kx squared. In this case, we're going from the equilibrium position, x equals 0, to the new position, 11.0 centimeters. So I just plug this in, 1/2 times 360 newtons per meter times, in this case, we're going to say 0.11 meters. Notice I had to convert it to meters, couldn't use it in centimeters. And now I square that, and I'm going to say 0 0.5 times 360, which is, of course, 180, times 0.11, which is 0.0121, I think, squared. And all of that gives me 2.178. And I am assuming that I had 2 sig figs. Oh, actually, the 11 was actually 3 sig figs, as was the 360. Let me fix that. So this should have been 11.0 meters like that. So now I got 3 sig figs. So I'm going to say this is 2.178 joules is the net work done, and I have to underscore the 8 because that's not a sig fig. So there's our part A. Anybody have any questions about that? For part B, we want to know basically how fast it will be moving. So with that one, what we know is the work done by the actual spring is the only work done. So for part B, W net equals work by the spring. And of course, the work done by the spring, or excuse me, the work done on the spring, is now the work done by the spring, and it actually has the capacity to do exactly the same amount of work as put into it. So I can say the work that we put into the spring is now going to do that much work in pushing the box along. Okay. So I'm saying W net equals, ooh, I evidently left off an R in the word spring. That's a neat new brain fart. Anyway, so work done by the spring. And obviously, that work done by the spring would be 2.178 joules. Again, we should round that to 2.18, but I carry one extra sig fig for all the intermediate calculations. So that's the total work done. But that goes into changing the kinetic energy of the mass that's attached to it or that's leaning against it by an amount delta K. And delta K, of course, is K final minus K initial. So we're going to say all this is equal to delta K. So I'm going to say 2.178 joules is equal to K final minus K initial. And of course, K initial was 0 because we had compressed the spring, then we sat a box right next to it, not moving, and then we let it go. So the initial velocity was clearly 0. This gives us two, or heck, I guess I'm just going to write one for some reason. 2.178 joules is equal to 1/2 times the mass, and we know the mass is 1.85 kilograms times V final squared, and that's what we want to solve for is V final. So V final is going to be, notice I'm going to take the 2.178 and I'm going to multiply it by 2. I'm explaining algebraically how I'm solving it, by the way, okay, rather than writing it. So I'm going to take the 2.178 joules. I'm going to multiply that by 2. That gets rid of the 1/2 on the right. Now I'm going to divide by 1.85 kilograms. So I took that answer, 4.356, which is what you get when you multiply 2 times 2.178. I'm going to take that 4.356 and divide it by 1.85 kilograms. And now I've got joules divided by kilograms, which gives you meters squared per second squared. So now I have to take the square root of that, and the square root of that would be the square root of 2.3546. I carried two extra sig figs this time, and that's meters squared per second squared. Again, remember I broke down a joule into kilogram meters per meter squared per second squared. Where was that? Oh, here. So kilograms meters squared per second squared. So if I divided this quantity by a kilogram, all I'd have left is meters squared per second squared. So that's how I got the units that are under that square root. And obviously, we could take the plus or minus square root, but there's no real need to. We were just going to call it positive. So now I'm going to take the square root of that number, which is the same thing as raising it to the 0.5 power, and I get 1.53. And carrying one extra sig fig is 4. So 1.534 meters per second, because the square root of meters squared per second squared is meters per second. Anybody have any questions on that? Okay. Now, part C is a little more tricky. It says repeat part B, but assume that the block is moving on a table and that some kind of constant drag force, 7 newtons, is acting to slow it down, such as friction or perhaps your finger. So, what we're doing is we're saying now, unlike part B, where the work net was only the work done by the spring, in this case, the work net is the work done by the spring in addition to the work done by this new drag force. So we need to calculate that new drag force so we can find out what that does to work, and then that'll give us a change in kinetic energy as well. And that's what we're asked for, is to repeat the same problem but with this new drag force. So we found that W net is going to equal W spring plus W drag force. So I'll say WFD. WFD, ooh, W, the work done by the drag force, is in fact acting counter to the motion. So the force is actually, let's say, backwards to the left, which would be in the negative x direction, and the displacement is forward to the right, which is in the positive x direction. And as we learned, that definitely gives us a negative amount of work. And I'm going to go ahead and start off by writing it negative, and then I'm just going to say, well, it's a constant force. It's going over a constant distance. So the work equals the integral of F dot dl just becomes F times L. Everybody hear that? This is a force whose direction is not changing. It's actually exactly anti-parallel to the dl vector, and it's anti-parallel for the whole time. So the angle is 180. So you can think of it as F dot L, which would be force times L times the cosine of the angle between them. The cosine of 180 is what gives us the negative. Okay. But the distance traveled is, of course, that 11 centimeters. So I'm now going to say it's FD times basically what we call x2. So this is going to be negative. The force is 7.0 newtons, and the distance traveled is 0.110 meters. So 7 times 0.110 is obviously negative 0.770 Newton meters, which of course is a joule. But now, because we multiply by 7.0 newtons, we only have 2 sig figs, so I have to underscore that 0. Now I've got the work done by FD, and I already know the work done by the spring, so I can say work net is equal to the work done by the spring, which we found was 2.178 joules, plus negative 0.770 joules. Remember, I wrote it as Newton meter over there, but we know that a Newton meter is a joule. So I'm going to take 2.178 and subtract from it 0.77. And of course, that only allows us to the second decimal place to be sig figs. So 2.178 minus 0.77 gives us 1.408. But that 8 cannot be a sig fig. And that's the net work done. Now, again, the net work is equal to the change in kinetic energy. So W net equals delta K. And delta K, of course, is K final minus K initial. But again, K initial was 0 because we started it from rest, sitting right up against the spring that's already been compressed. So now we can say that, oops, left it in red. So now we can say that K final is equal to W net. And that means 1/2 mv final squared is equal to 1.408 joules. Hopefully you guys followed the algebraic operations I did before. I'm going to again explain it, but rather quickly. So I'm going to take the 1.408. I'm going to go ahead and multiply that by 2. So 1.408 times 2 is 2.816. Now I'm going to divide that by the mass, which is 1.85. So I'm going to say divide by 1.85. And now I've got V final squared is equal to 1.522. So I got to take the square root of all that, 1.522. Notice that second 2 is an extra sig fig. Notice also that the units would be meters squared per second squared. And now I'm going to take the square root of the 1.522. by raising it to the zero point 0.5 power, and that gives me 1.234 meters per second is equal to V final. So because there was this dissipative force or drag force, we couldn't reach the same speed, or the mass couldn't reach the same speed by the spring pushing it. So instead, the spring reached only 1.23 meters per second instead of 1.53 meters per second. Any questions on that? All right. I think that, yeah, that's plenty. We've done quite a bit, of course, on uh, the work energy theorem and work in general. So it's time to go ahead and move along to chapter 8. Does anybody have any questions about that? I'm going to go ahead and open up chapter 8 homework. You'll see that's on your new weekly module. So the module for this week, both in my NO2B and my 001B class, will both have the chapter 8 assignment. You'll notice also, I think it was chapter 6 might be due like July 3rd. That's still this week, so I went ahead and posted that in there as well, even though it's already in a previous week. And chapter 7 is, of course, I think that's due on the 7th, but chapter 8 will be due. I doubt there's obviously no chance we're going to finish chapter 8 tonight, so it's not due this weekend. It'll be due at least the following weekend. Anyone have any questions on that? All right. So, conservation of energy is where we're going next. That's chapter 8. And I want to tell you a little bit about conservation of energy. As I was saying earlier, work gave us a way of calculating certain things, and specifically, it gave us a way of calculating things without using vectors so much. Now, I had to teach you about doing a dot product, so obviously we went deeper into the woods of vectors. But once I did that, we were able to find a new quantity called work that would be a scalar quantity. And if someone gave you an amount of work done, then you could obviously get around solving the physics problems without actually doing vectors. But if you actually had to calculate the work, there's obviously some vectors that have to go into that in most cases, or sometimes you'll luck out and just have a force that's exactly parallel or exactly anti-parallel to the displacement, in which case you don't have to do any dot products or anything like that. You're just, using the idea that at anti-parallel, the cosine of 180 is negative 1, and at, parallel, the cosine of 0 is 1. Okay? So we're moving on now to do this with this new quantity, energy in general, and specifically we're talking about what we call mechanical energy. So mechanical energy turns out to be essentially potential and kinetic energy. So we're going to have an energy associated with position, which I talked to you a little bit about last time by talking about a uh, turtle that you find sitting on top of a fence post. Again, a really cruel thing to do to a poor turtle. Don't do that. But either way, the main thing is when the turtle is up, let's say a whole meter off the ground, then it has the potential to drive a nail. Because it has that potential, we have decided to create this idea of a potential energy, and energy is another thing that gives you the ability to do work. So what we're saying now is the turtle existing on the top of the pole gives that turtle a certain amount of potential energy, and that potential energy is going to turn out to be m times g times h, where h is basically measured from some arbitrary height, but as long as you stick to that arbitrary height each time you do it for a particular problem, it doesn't matter that that arbitrary height is arbitrary. Okay, so m times g times h, as long as we're not super far from the center of the earth or from the surface of the earth, more specifically from the surface of the earth. So if the distance from the surface of the earth to an object is on the order of the size of the radius of the earth, then you have to use some other version of potential energy. But the one I just said, U equals mgh, is acceptable if it's not a large fraction of the radius of the earth away from the surface of the earth. So we're going to start off with section 8.1, which is conservative and non-conservative forces. Section 8.2 is potential energy. Section 8.3 is mechanical energy and its conservation. Section 8.4 is problem solving using conservation of mechanical energy. And 8.5 is the law of conservation of energy. 8.6 is the conservation with dissipative forces solving problems. And 8.7 is gravitational potential energy and escape velocity. So that's kind of neat. That's actually going to give us a way to calculate the potential energy, even if the object is a appreciable distance from the surface of the Earth or from the surface of the Sun or from the surface of Jupiter or whatever. Yeah, Jupiter sort of doesn't have a surface, but you know what I'm saying. 8.9, potential energy diagrams, stable and unstable equilibrium. I definitely want you guys to make sure y'all read all this stuff. There's a lot of concepts that you're supposed to get from the reading that I'm just not taking the time to teach you because the concepts are interesting and they're important and that's what you need to learn. But you guys need to learn how to solve the physics problems, and that's usually the part that's more complicated than, in most cases, the concepts. And then finally, the last section is gravitational assist or a slingshot. Okay, so that's again something nice to read. Normally, what I do with my conservation of energy is I make it a lot shorter because I introduce my own conservation of energy equation, and then I show you a couple really drastic problems that shows you exactly what each term is. So that's probably what I'm going to do today. Even though it seems like a really long chapter, we can still knock out the chapter pretty quickly. So let me start off by reading the bold print definition of conservative force. Uh, and I'm going to just read this whole first paragraph. It says, we will find it important to categorize forces into two types, conservative and non-conservative. By definition, we call any force a conservative force if the work done by the force on an object moving from one point to another depends only on the initial and final positions of the object and is independent of the particular path taken. So that's a lot of words, right? But it's saying something very important. If you imagine calculating work, which we know the formula for work, work equals the integral of f dot dl, and it's a path integral, and it's a line integral, and we got to make sure we put the integrand and such a way that the variables signify that we're on that path, and we either got to let the dl or the limits of integration show exactly which direction we're going, all that good stuff. Yeah, that's all very complicated, but the main thing is what we're saying is there, if the force is conservative, then if you do work and going from this spot right here, which is A, to this spot right here, which is B, you can do it as a straight line, or you can do it with some crazy path like this and end up back at B. And no matter what, which one of those infinite number of paths you take, you'll always get the exact same answer. And not only that, it turns out that that exact same answer is only dependent on the initial and final position. So, for instance, if you had, x1 considered to be the x coordinate of the initial position and x2 to be the x ordinate of the final position, then your actual answer would be like f of x1 minus f of x2, or u of x1 minus u of x2, or u of x2 minus u of x1, or f of x2 minus f of x1. Doesn't matter, but the main thing is it's going to be something that only depends on the initial and final positions, and whether you chose to integrate it along a straight path or along a curved path or a hyperbolic path, whatever, you're always going to get exactly the same result. Okay, so you can imagine that's a really big deal. How could you possibly find a force that would do that? And it turns out there's quite a few of them. Okay. And in fact, I'm going to give you a bigger picture of exactly what happens with these forces that are conservative. And once you figure out, for instance, one way to test whether a force is conservative, once you've done that, then you'll get a list of other facts that are automatically true just because you've done that. So, here's another definition of a conservative force. It says a force is conservative if the net work done by the force on an object moving around a closed path is zero. So this time we're not going from A to B. we're going from A, doing some crazy stuff, doesn't matter what we're doing, turning all around like this, wee, 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 but we're ending right back up at A. If you do that, a force is conservative if the net work done by the force on an object moving around a closed path is zero. So if you actually go from point A to point A again and you found out the total work done was zero, guess what? The force that did that work was in fact a conservative force. So that's another one. So we now see sort of three things really. Specifically, remember the first definition said work done by the force on an object moving from one point to another depends only on the initial and final positions. That's a statement all by itself. It literally says something along the lines of work equals the integral of F dot dl from integrating from A to B. Well, it's saying that that is exactly equal to some u of B minus some u of A. Notice it only has the A and the B in it. It didn't tell us what path we traveled or anything. It only has the A and the B in it. That's a whole statement by itself. So that first part of the declaration of what a definition of conservative force is, the work done by the force on an object moving from one point to another depends only on the initial and final positions. That's a whole statement by itself and is independent of the particular path taken. Okay. Well, guess what? That also happens to say, well, it also doesn't matter which path we chose specifically because it only depended on A and B, right? So there's sort of three things at work here. In this case, we had UB minus UA, which hopefully are understanding because I'm using the symbol U, and U is the symbol we use for potential energy. And in fact, UB minus UA would be final position potential energy minus the initial position's potential energy. Okay, that's exactly what the integral is supposed to be, and it is independent of path. And then this other statement says a force is conservative if the net work done by the force on an object moving around a closed path is zero. So again, that's a whole other thing. Uh, in fact, there turns out to be a lot of stuff. So let me go ahead, rather than talking, which is, I think, important for you to understand and hear these words because sometimes reading doesn't come across as clearly as just hearing the words. And hopefully my explanations made it a little more clear, but they might have made it worse. Hope not, but maybe they did. So let's start off with chapter 8, conservation of energy, and I'm going to write down some of the stuff we just said. Okay, that's what we're talking about. So I'm going to go ahead and give you those facts that I told you that turn out to all be true, and I'll also hint at another. But anyways, it turns out F is a conservative force. That's one statement. If that's true, then all these other statements getting ready to write down will be true as well. Additionally, if any one of those are true, all the other ones will be true as well. Okay, so it's not just that this one has to be true, it's any one of these being true makes all of them true. Okay, so that's one. F is a conservative force. Two, and this is a highbrow version of showing that a force is conservative, specifically some crazy vector calculus. It's del so that's a vector operator. Notice it looks like an upside down triangle, like the delta symbol we had before, and hence we call it del. Uh, there actually are some people that I've known that speak Portuguese, and they call it nabla, Nabla. Don't know why I know that. Don't know why they told me that. Talked to a student in my class just Monday, and he had no knowledge of that, and he speaks Portuguese. So, anyways, but this del, if you take a cross product of that with F, and you get that it's identically zero, so I'm putting a triple equals bars there, is equal to zero, then that is another thing that's true. Now, I'll explain later what that is, but this is also called curl, whoa, no, of f is 0. So that del cross f that I just showed you there, that's also an operation called the curl. There's another operation called the divergence that looks a lot like it, except that would be del dot f or del dot b or something like that. This one's a cross product though, so it's a little more complicated, and we'll get to it a little later. There's a third one, and it says the integral f dot dl from A to B, which hopefully y'all all recognize that that is the work done in going from A to B, is equal to some function of B minus that same function of A and is independent of the path. So I could write this down as a fourth statement that says the integral from A to B of f dot dl does not change when the path taken changes. Okay. So that's how I broke it up into two separate statements, even though it was listed as one statement in that opening paragraph definition of conservation of a conservative force, excuse me. I broke it up by writing 3 and 4 there. Okay. Now, 5 says the integral, and here's something fancy. You're going to make use of this later. You can take a integral symbol and put a little circle on it, and that tells the world, hey, this is the integral of, if it's a single integral, it's the integral of a closed path. So it's some integral you did starting at point A, and you went all these crazy places. Doesn't really matter what you did, but you went somewhere and came back and ended up at A again. So the integral, the closed integral of f dot dl is equal to 0. So that's another equivalent statement. So remember, the idea of this is if any one of these is true, all of them is true. So we're really learning a whole lot of stuff from this, and it's partly due to really some great minds in the past. But anyways, we'll learn more about this as the semester progresses, as well as the second semester progresses. So now that we've got that, we can also make a sixth statement. It says, uh, here's a mathematical symbol. It's a backwards, upside down E. Okay. What that means in everyday language is there exists a scalar function U. Now that's another fancy mathematical symbol. That looks like a backwards T. Okay. It's actually supposed to be a cursive ST for such that. So there exists a scalar function U such that the integral, or such that f is equal to the negative gradient of U, like that. So I'll write it in English. There exists a scalar function it's supposed to be the word function, but it just went to crap. There exists a scalar function U such that f is equal to the negative gradient of v of U. Okay, so this quantity is called the negative gradient of u. Okay. So that's pretty amazing. And it's actually the fundamental idea behind these conservative forces. So conservative forces can be thought of as forces that conserve energy, but they can also be thought of as forces whose curl is zero, or forces such that any closed integral is going to be zero, or forces such that the work done by this force along any path is independent of the path and only depends on the initial and final positions, all that good stuff. But it specifically says, hey, there is a scalar function that you can use instead of dealing with the vectorness of the of nature. Okay, there's a scalar function that you can use as a stand-in for this force F, and that scalar function is what we're going to call our potential energy U. And once you figure out what that U is, you can use it to get the original force back out. So if you happen to discover a potential energy function like U to begin with, you can easily figure out exactly what the force that caused it was by taking the negative of the gradient of U. So now, I will tell you also that there's something related in here. I would normally put it as 7, but it's not exactly. I don't want to take the time to do all the legwork to figure out exactly all the mathematical bells and whistles I have to put in it to claim it. But I will tell you that if you've taken differential equations, there's a equation called an exact differential equation, and it's written like, some function of x and y times dx plus some other function of x and y times dy is equal to zero. And when you run into that type of differential equation, what you learn in your differential equation class is you take the derivative of the function that's in front of dx, you take the derivative of that with respect to y, and then you take the function that's in front of the dy and you take its derivative with respect to x. And if you find that those two derivatives after you take them are equal to each other, then the equation is exact. Well, it turns out that in some sense, the that differential equation is true because it came from either a scalar potential or a conservative force. Okay, and that's going to be a really big thing when you take, for instance, engineering thermodynamics. You'll write a lot of times where you'll just write out how one variable changes when another variable changes, and you'll write it as some expression times dx plus some expression times dy equals zero, and all of a sudden, all this stuff will come back together and hopefully make some sense. Anybody have any questions on that? Now, we only got a couple minutes left, so I thought I'd go ahead and show you exactly what those dells are. Not because I'm going to make you do it, but I just don't like, leaving that stuff in the ether. So, first off, I'm going to say the del operator. It's something that's meant to have something right here. So, often we'll write del with a little space next to it, or maybe three dots like you see there. That means I'm supposed to put something to the right of it. Now, that something might be a scalar function, in which case I'm going to call this the gradient of that scalar function. But that thing that I put to the right of it might be a dot for a dot product, in which case I'm calculating the divergence. Or to the right of that, I could put a cross for a cross product, and in that case, I'm calculating a curl. And in both cases, the divergence and the curl one, you also have to add a vector function. So it's del dot D or del dot E or del dot F or del cross E or del cross D or del cross F. But this operator can be thought of as just a plain I hat. And then to the right of the I hat, you take a derivative. Notice that weird backwards six looking thing that I just wrote there. This you will not learn until Calc 3, but it's called a partial derivative. And it's really, really simple. Like I've already showed it to you in your lab for propagation of error. But it's basically pretend like all the variables that's not in the bottom of that derivative, pretend like all those are constants, and then I'll take the derivative with respect to x. Okay. That's for this first term. So notice I got again a little spot because we're expecting whatever's to the right of that triangle is going to be to the right of this dx, and therefore we're going to take the derivative of it. It also has a j hat, and then you're taking the derivative with respect to y. And it also has a k hat, only now you're taking the derivative with respect to z, and again, you're expecting something to the right of it. That's what that del operator is. If you had, for instance, f of x, y, z equals 2xy plus 3xz plus 4yz squared, then del f equals the gradient. Ooh, or I could say the gradient for f. And it would specifically equal, I'm going to take the derivative of 2xy plus 3xz plus 4yz squared with respect to x. And for that first term, 2xy, I'm pretending like the y is a constant. So the derivative of 2xy is just 2y. So I'm going to say 2y. Now, the second term, the derivative of 3xz with respect to x, the z is supposed to be a constant, so the derivative of 3xz is just 3z. So I'm going to say 2y plus 3z. The 4yz squared has no x in it whatsoever, so when I take the derivative of that, I get 0. So now I've taken the complete derivative with respect to x. I'm going to put the I hat right next to it, just like this term says. Now I'm going to take the derivative of it with respect to y, and in this case, I'm going to get 2x plus 4z squared. And that's going to be the j. And finally, I'm going to take the derivative with respect to z. The first term has no z, so that's going to be 0. The second term has a 3x times z, so the derivative of that with respect to z is just 3x. And the last term, 4yz squared, the y is supposed to be a constant. When I take the derivative of 4yz squared, I get 8yz. So plus 8yz k hat. So that's what the gradient does. You can imagine some other stuff it might do if I were to show you what the divergence is. And just quickly, it looks like this. Del dot f equals the partial of f sub x. Notice that f is a vector, so it actually has a component f sub x I hat plus f sub y j hat plus f sub z k hat. So it actually has an x component, y component, z and z component. And since we're doing the dot product, the x term only acts on the x one. So it's the partial of f with respect to x plus the partial of f sub y with respect to y plus the partial of wrong f partial of f sub z with respect to z. That's what the divergence is. Uh, and then the curl is del cross f, which you guys haven't even learned this unless hopefully you learned it in trig or pre-calculus, the trig part. Basically, what you do is you take a determinant of a matrix, and the matrix that you're taking the determinant of has the first row being I hat, j hat, and k hat. The second row being the first vector in the cross product. So in this case, it's the del. So I'll write it as the partial with respect to x, partial with respect to y, and partial with respect to z. And then the third vector is the second vector in the cross product. So that's fx, fy, fz. We're a little early to show you exactly how to compute that determinant, so I'll leave that be. But that's it. I'm going to go ahead and call it a day. I think I've probably knocked your socks off with all this math stuff. We'll jump into chapter 8 next time on Monday, and that should actually be enough. I'm going to post a lot of videos on chapter 8 so you can see a lot of examples, but it's really pretty straightforward. This is supposed to be an easy part of the course, chapter 7 and 8, except for the complications that arise from learning a dot product and learning to do a path integral. So you guys are free to go. Go ahead and chat me your first and last name if you haven't already done so. Remember to include the fact that you're in N02B if you're in that class, or the class, if you're in the other class, the O01B, put that down, or you could just say it, the online class or something, or asynchronous, whatever you want. Thanks again, everybody. I appreciate you coming. I wish I wish I had a little bit more interaction. But it might have been because I steamrolled you because I was sort of excited about covering this stuff and just talked and talked and talked. So feel free to slow me down and talk to me. Thank you for coming.
I just had a quick question.
Yes, ma'am.
What's your late policy with like turning in the labs late?
If you get it in before I actually grade it, I don't even take points off usually.
Oh,
I,
okay.
I don't require that because I didn't put it in the syllabus, but that's pretty much what I do. Uh,
Okay.
so just, yeah, get it to me before I grade it, and it's probably not going to harm you at all.
Okay, thank you so much.
You're welcome. Anybody else? All right. Well, guys, I'm exhausted. I've been moving my mother-in-law out all day today, and I am just tired, so I'm going to call it a day. Feel free if you need more time. I'm not going to hold the office hour this time. I'm just too exhausted, but feel free to send me a text, and I'll answer questions probably for the next couple hours anyway. So have a good day. Thanks for coming. Bye bye. Bye bye. See ya.